Beth.
And I'm Beth.
Welcome to Physics with Beth
and Beth.
Hello, and welcome to Physics with Beth and Beth. I'm Beth. We're in this AP Physics 1, Unit 7, Oscillations unit. Today we're going to be talking about simple harmonic motion. We're going to have one video understanding the concepts behind graphing simple harmonic motion. Then we're going to follow up with a second video after this one about graphing and translating position time graphs, which we're going to be working with today, into velocity versus time graphs and acceleration versus time graphs. Then one more video on how to do problems with these once we've mastered graphing. Okay, so we're going to just get started. I wanted to explain what we've got. We've got a spring here hanging vertically. We also have a spring that's horizontal. And then we have a pendulum. This is going to apply to all three. And if you can see this, I'm going to talk about positive position, equilibrium, and negative position. So equilibrium line is where the spring would just be naturally hanging and it's not compressed nor is it stretched. Here, equilibrium, where it's naturally at. It's not stretched. Here's equilibrium. It's not compressed. And we're back to equilibrium. Okay? So that's equilibrium. Then we're going to talk about an amplitude. An amplitude is the maximum distance from the equilibrium line where it would naturally hang. So amplitude here, we have the maximum distance from the equilibrium line. Here, this is maximum distance from an equilibrium line, and then we're back to maximum distance. And this would be one cycle because we would start compressed, then equilibrium, then stretched, then equilibrium, and then compressed. Over here, we would start stretched to equilibrium, to compressed, back to equilibrium, and then to stretched again. All right, it's important to note in these graphs that our positive position is above the equilibrium line and negative position is below the equilibrium line. When you're dealing with horizontal, positive position is to the right of the equilibrium, negative position is to the left of the equilibrium. In a pendulum, works the same way. We're just going to talk about springs today. But in the pendulum, we start here on the right, and here's equilibrium. Then we swing to the left. We go back to equilibrium and then back to the right. And positive position is to the right of equilibrium and negative position is to the left of the equilibrium line. And this is your equilibrium where the pendulum would just hang straight down. Okay, we're going to get started. I have labeled these positions A, B, C, D, and E. All right, those are our positions we're going to talk about. Remembering amplitude is the distance from equilibrium line where the distance is a maximum from that equilibrium line. So here we have A. We are at a max distance from the equilibrium line. So our amplitudes would be A. C, we're also at a max distance from that equilibrium line. Here is my equilibrium line where X is 0 degrees. Right here, and I have positive position and negative position. All right, and remember I said, hey, this one was at negative position. Well, I am showing that I'm in negative position at C, but it's still an amplitude. Maximum distance stretched, and so is E. So that's going to be ACE. Now, my equilibrium line, what points are on the equilibrium line? B and D. So that's going to be, and I'm going to just erase this, B and D. And that's where X is equal to 0. Right here at equilibrium. Okay, now we're going to talk about some concepts. What you need to know is that at amplitudes, velocity is equal to 0. And you're like, well, how do I know that? Because it starts at rest here. It's starting at rest. It's moving, but it stops when it gets to this maximum amplitude. It stops to turn around and it goes up and it's compressed. Then here it's going to stop and to go ahead and continue the cycle over and over. It's a repetitive. All right, here I'm stretched. I start at 0 velocity and I'm at an amplitude. I go to equilibrium, I'm moving, and then I go to this max here, another amplitude, max compressed, and it's going to stop to turn directions to go back to equilibrium, and then it's going to go to stretched. It's going to stop here to turn directions to complete the cycle. So velocity is 0 at my amplitude points, which is A, C, and E. Now, then that means if velocity is 0, your kinetic energy is 0 joules. This is 0 meters per second. What about my potential energy though? The potential energy of a spring is 1/2 times the spring constant times the distance stretched or compressed. Well, at A, we said this is an amplitude. I'm at my maximum distance stretched or compressed. So that means I'm going to have a maximum potential energy of that spring. Now, force of a spring is that spring constant negative times the spring constant times the position. Again, at my amplitudes, I'm at my maximum distance stretched or compressed. So that X is a maximum. So if X is a maximum, then that means force of a spring is at a maximum. All right, I'm going to abbreviate that max. Now I look at my acceleration. Okay, well, F equals ma, Newton's second law, right? I just put it like how it is on your equation sheet, actually. It's force divided by mass. Well, if force is at a max, which we just determined, then that means acceleration has to be at a max. Okay, perfect. Now, the mechanical energy, it's important to note that the mechanical energy of a system, we're starting here, we said, with potential energy, and that it's at a max. And it's at a max because there's no kinetic energy. It's zero because it's not moving at this amplitude. So that means it's all potential energy. Well, our potential energy of our spring is 1/2 k x squared. Well, we're going to replace x because we know that's an amplitude. And by the way, we use a capital A for amplitude because we're going to be using a lowercase a for acceleration. So our mechanical energy of our system is 1/2 the spring times the spring constant times the amplitude, that distance, that maximum distance compressed or stretched, squared. And that's going to be the mechanical energy of your system. And it's going to remain the same. Let's say this came out to be, I gave you numbers and you figured it out, and it came out to be 12 joules. Well, that means at any point along, at B, D, any point in between all of these, it has to total 12 joules. Okay, because that would be the mechanical energy of the system. All right, now let's look at what's happening at equilibrium. At equilibrium, let's go with our potential energy of a spring first. We have 1/2 the spring constant times that distance stretched or compressed squared. Well, at equilibrium, we said x is 0. It's on the equilibrium line, which is 0 meters. So then your potential energy is 0. Now, we know energy can't be created or destroyed. So what happened to it? Well, it converted all to kinetic energy. If we didn't lose any to friction, thermal energy to friction, which we're going to say that we're ignoring friction here. So that means all that potential energy went to kinetic energy at point B. All right, so that means your kinetic energy is going to be a max because there's no potential energy of the spring at B and D. And if kinetic energy is a max, that means your velocity is at a max. All right, now we look at force of the spring. We're at equilibrium still. All of these are for equilibrium. Well, if the force of the spring, we said that it's K, spring constant, times our position, and the negative of that because it's a restoring force. Well, we said at equilibrium, x is equal to 0, so that means force of the spring is 0. If force of the spring is 0, that means acceleration is 0. All right, so that's what's happening at our points A, C, and E at amplitude. Velocity is 0, it's at rest to turn around and change directions. That means kinetic energy is a 0. That means your potential energy of a spring, your force of a spring, and your acceleration are all at max. At the equilibrium lines, we know that velocity and kinetic energy are at a max, and your potential energy, force of a spring, and acceleration are all equal to 0 because there is no distance stretched or compressed at the equilibrium line. X equals 0. All right, and it works the same way for a pendulum. It would just be here in the middle would be x equals 0 where it hangs straight down. Not moving right, not in a right position or a left position. And it works the same here. At equilibrium, these two are at equilibrium points, and these A, C, and E are all at amplitude points. Now, that begs the question, what's happening in between here? All right, well, look, you have, let's pick this point right here. It's in between this potential energy at a max and the kinetic energy at a max. And here, potential energy of the spring is 0, kinetic energy is 0. These are all at point A, and this is at point B. So what's happening in between here? Well, look, it's moving. It's not at an amplitude where it's stopping to turn around. So we know there's kinetic energy. What else is happening? Oh, wait, it's got a distance from the equilibrium line. So it has to have potential energy of the spring too. So any point between A and B has both. Any point between B and C has both kinetic energy and potential energy of the spring. Same with C and D. Any point between here and any point between here is going to have kinetic energy and potential energy of a spring, because there's a distance from the equilibrium line. So there's an X, and it's moving. It's only stopping at the amplitudes to turn around. All right. That's all I have for the concepts of simple harmonic motion. These are really important to understand, and not to memorize, but to actually understand so that you can pull it out, this information, for multiple choice questions or something like that. Okay, I hope that helped. If you like this video, we would love for you to give us a thumbs up, subscribe, or share with one of your physics peers. And thank you for watching, and happy physicsing.